So let me remind you of a couple of things we saw last time. So last time we started studying random walks. And let me just start right away by emphasizing that random walks looks like a different process. We are studying now some random, like real-time particle moving and drawing some trajectory where it has some probability of moving at each step. So you could think that it doesn't look like we are doing statistical mechanics in the same sense as the first half of the course, where we're summing over configurations and weighting each configuration with some energy functional. So it does look a little bit different. Both are about statistics, about summing over many configurations. But in one, we had a table, and we had some temperature, and we were summing over all possible configurations of the table. And in the other problem, we sum over a walker that is moving in some trajectories, and it doesn't look like the configurations of energy of some physical system. So let me just clarify that there is not such a huge difference between the two, that it is just a question. Of course, the problems are different if you are really studying random walks, like particles of smoke going around in a room versus a spin system. Of course, it's not the same thing, but it's very much related. And for example, one way of saying is one object we considered was we had some probability of going from position 0 to position R, and we constructed this that I would call a grand canonical partition function. It's a sum over walks of all possible sizes. They are weighted by some chemical potential mu to the n to keep track of the size. And then we sum over the probability. So of course, if you know this object, you know Pn, because you just take the coefficient of mu to the n and you know Pn, right? So this object has all the information about paths of any size. And conversely, if you know paths of any size, you just sum them up and you get this object. Right? Now, just remember that what is the probability of going from 0 to R? This probability is just how many paths there are, omega n, that go from 0 to R, divided by the total number of paths, which would be z, a partition function. Right? So this would be what the probability is. It's just total number divided by partition function. Right? So this object here is what? It is just summation over n, 1 over how many configurations there are with length n, and then something like exponential of log mu times n, that I'm just writing mu to the n in this exponential way, plus log of how many ways there are of connecting 0 and R. And of course, now it looks more like a statistical mechanical model. What would be this? What could be some model described by this? It could be a model where we say that, for example, we have molecules, right? And these molecules, there is some cost for building a long molecule. So there is an energy cost, which is just the length of the molecule times some chemical potential. Right? That's the energy of building a big molecule. Each link costs some energy. So this would be some energy cost of raising the molecule. Right? And this could say suppress long molecules. I put a solution, a chemical solution, and a long polymer starts forming, but it costs energy, so it would suppress the creation of these long molecules. But what is this term here? Tells me that on the other hand, there is an entropy enhancement, because there are many ways of forming these molecules. And therefore, there could be an interesting equilibrium where entropy fights against energy, and this could describe some long molecules that are described by some random walk. Okay? So from that point of view, what was before some real-time dynamics of a particle or some statistical mechanics of some long molecules would be exactly the same. Of course, real molecules, what would be most natural for a more realistic molecule is for it not to self-intersect. Because if it's, say, a polymer, it will not want to be at the same position. So that would motivate us to consider, even if you want even more realistic, we could consider what are called self-avoiding walks, which are walks that do not intersect. Then it would be even better from a chemical point of view. And you could wonder, does it matter if they self-intersect or not? Because, for example, for the random walk, it did not matter if the probability was a Gaussian, or if it was nearest neighbor jumps, or if it was a circle. It was all the same in the same universality class at large distances. So you could also wonder, perhaps not intersecting is also in the same universality class. It will complicate the initial computations, but perhaps at large distances it is the same thing. Yeah. So that's not true. One could wonder that, but it's not true. Luckily, there are different universality classes. Things are different. So, for example, what was particular to the universality class that we found was that there was a critical exponent, 1/2, for what is the typical size of a walk as a function of n steps. And this defines this critical exponent that was 1/2. And we will see that the nu for the self-avoiding walk is close to 3/4, which is bigger than 1/2 in 2 dimensions. So just as a friend. And that's intuitive, because if a walk cannot self-intersect, it will be longer, because it cannot just go back and stay close to the origin, because it can't self-intersect. So it needs to open up more. So it is something in between 1/2 and 1. 1 would be the straight line. 1/2 is the random walk. And something in between 1/2 and 1 is indeed what we have for the self-avoiding walk. Okay? So it's good. So what did we see about random walks? One way of seeing this UV and IR is just very explicitly computing this mean displacement as a function of the number of steps. And we computed it. We got this. I just did the computation a bit slower here, but this is the result. And we see that if we have a very small bias, we could be in the regime where n is much bigger than 1, but still the bias is so small that the bias is still much smaller than 1/n. Then you can ignore the second term, even though it is n squared, because the bias is very small, and your behavior is approximately a square root. But eventually, n takes over, n becomes very large, and then it crosses over to a linear regime. So this would be the statement that if I am at distances that are, if my bias is very small, right, then or if I say differently, if sigma is very large, then at distances much smaller than sigma, I don't see the bias, and it looks like a regular random walk. But as I start zooming out, that is coarse graining, I realize that actually there is some privileged direction, and these paths as a cross grain are becoming longer and longer. Right? And here I emphasize again this step. There is a step of integrating out, which means that you sum n steps and make it into one step. But then it's hard to compare this and this. So what do we do? After we integrate out, we rescale such that they have the same average step size. And now I can compare this and this. And then I could coarse grain again and go here, or I then rescale. But the point is that it's becoming flatter and flatter. Whereas if I tune to R0 equals 0, no bias, I would do RG flow and stay in the same point. So that's what you would have to do as an experimentalist. This R0 is a relevant operator. It's like you have wind. You are doing a random walk, but you have some wind. Some window is open. What do you have to do? You have to put a fan to fight that wind, and you have to tune the fan. And if you tune it right perfectly to fight the wind that comes from the window, you get a beautiful random walk here of your smoke particles. But you are never going to do it. You will be failing by a little bit. So eventually you will see that that there will be some small bias. Okay? So you would have to fine tune. And how many parameters do you have to fine tune? It depends. Here we have one relevant operator, so you would have one knob, which is the button of your fan. You just have to turn it. You have power 0, 1, 2, 3. Hopefully there are intermediate powers, otherwise you're screwed. But okay. So you would have some van that you would tune, and it's a single knob because there is a single relevant operator. In other models, where you approach a critical point, like for example in a magnetic material, often you have two knobs. That would be the temperature that you can tune, and say the pressure in a gas, or the temperature and the magnetic field in a magnetic system. Okay, and those would be the two relevant operators. One more comment. So I made a comment on going from random walks to more conventional statistical mechanics. Let me just make one comment about going from the more conventional statistical mechanics, like the Gaussian model. Just one comment on how we would go about trying to prove this relation, but not starting from the random walks going here, because this we did in the lecture, right? But how we would start from the Gaussian model and guess that it has anything to do with random walks, right? Because we did the converse, right? So we started with random walks, we computed this, and we saw, oh, by the way, this is just a geometric sum. I sum it, and I get the propagate. Right? That's what you did in the tutorial, right? So how would we see some signs of random walk inside the Gaussian model already? So one way of seeing it is noticing that what's the Gaussian model? The Gaussian model, when we compute correlation function, what are we doing? We are computing correlation function at our table displacement at 0, and then table displacement at r. Right? And this is the integral of, I put here x0, xr, and then I have exponential of an action that I'm going to write like this. There is a minus a sum over all sides of my lattice, xi square, minus b sum over neighbors of my lattice, I and j, xi, xj. Now, do you recognize that this is our table? Our table, we did not write it exactly like this. We wrote an x squared term, and we wrote an xi minus xj squared term. But the xi minus xj squared term contains xi, xj, and xi squared. So it is just redefining this a and b. Right? Do you agree? So this a and b is the same as our table. But now we can do something, we can do a trick. We can think that this is our Gaussian term, this a, and I will think of b as some kind of perturbation. Right? Now, what does it mean that I consider b as a perturbation? I just expand it down from the exponent, and I have to compute all the terms in my expansion. So let's treat the leading term. I just put b equals 0. Right? The first term. I get 0, because this is even, and I'm integrating over x0 and xr. Right? So we get 0 right away. Now I bring down 1 power of b with the term x0, x1. Now x0 becomes x0 squared. It's no longer 0. Right? But x1 is 0 because x1 is alone. So we see that when we bring down b, we need to bring down enough b's to connect point x0 and xr. We need to bring down a bunch of b's that connect all the way x0 and xr. Otherwise, just because I'm integrating an even function, the integral over x0 is 0, the integral over xr is 0, and the integral over any xi of an odd power of xi is 0. So immediately I see that if I treat this b as perturbation and expand it down, what I get is that I get a sum over paths that connect 0 and r. Right? Weighted by some b, which is related to our effective mass. But that's exactly what you had, a sum over paths of mu, where mu was somehow related to the effective mass. Okay? And that's how we would make contact to what we had seen. Okay? So here, if you just copy this, you understand nothing, right? So you have to put some more words. But, was it clear? You just treat this b as perturbation, and you need to make a ring of b's. Otherwise, just by parity, you will not get in. So it's exactly the same type of argument that we have seen twice already in our high temperature expansions. Yes?
What will the critical exponents be in the table case? So you have nu equals 1/2 and 1 in the random walk.
Yes.
Which are those in the table case? Is there like a one connection that it's easy to see, or?
That nu equal 1/2 is just related to the fact that the propagator has m squared minus k squared. It's just how the propagator vanishes. That will be the translation to the k squared. Okay. Good. So now, so this was a little bit, of course, again, going from here to here was totally clear. Oh, now, okay, it's an equality. Of course, we did not need to do this. I'm just telling you, how could we have guessed, if we did not think first about random walks, that the Gaussian model had anything to do with walks? And this is one way of seeing it. We treat the term that jumps, that connects I and I plus 1 exactly as a perturbation, then that is the term that walks by bringing it down. So okay, yeah, that's it. So today then we are going to study self-avoiding walks. They're much more interesting because these are walks, even on a lattice, that cannot self-intersect. So it would be something like this. So you see that cannot self-intersect. So how many are there with n steps? So this is the number of self-avoiding walks with n steps in a square lattice, say. Well, let's compute for a few n's. So when n is equal to 1, with one step, how many paths there are? 4. I can go up, left, right, 4. What about 2 steps? I go 4, I choose one direction, and then 3. So 4 times 3. And then so this 4 is just I choose a direction. Then here I choose a direction, and then I have 3 directions. So I pick, say, this one. And then 3 again. 4 times 3 times 3. And next it's hard. Because then for the first time I could be in trouble. Now then it depends. If I choose going this way, there are 3. But if I choose going like this, there are only 2 options. So this, it starts to become hard. So this is a hard problem indeed. It's hard. Everyone is. Yeah? So this is in contrast with the usual random walk. For the usual random walk, the number of paths with these steps, it is just at each moment I can choose twice the dimension in an hyperlattice to the power n. So what do we expect for this mn for the self-avoiding walk? So let's first establish the following, that mn, it's definitely smaller in d dimensions. Now I'm doing here a d-dimensional hypercubic lattice. Then this number of walks is definitely smaller than this type of walks that we were doing in the beginning, which was first I pick 2d, and then at each step I pick 2d minus 1 to the power n. Right? So this is definitely a bigger set of walks. It contains the self-avoiding walks, right? Because at each step definitely I cannot go back, but it contains more walks. Right? So this is definitely true. And this is bigger, for sure, than saying that if I am in d dimensions, I always go in the direction of one quadrant. So I always go, say, instead of left and right, I choose always right. Instead of up and down, I choose always up. Instead of front back, I choose always front. So I go only in one quadrant, right? In one octant in 3 dimensions, and in one d version of that in d dimensions. So that would be, at each step, I choose d to the n. And we could even, okay, so it would be bigger than d to the n, and this would be walks where, say, in 3 dimensions, at each step I choose one direction to go, but positive always. So by definition, right? I'm always moving in this direction of the blackboard. So it never self-intersects. I could even make a little bit better if I want to say that I could first choose the quadrants. So I could put here number of quadrants and then do this game. So how many quadrants there are? Oh, it's obvious. So it's 2 to the, for each direction I choose this side or this side, right? So 2 to the d. Yeah. Right? So this is a definite equality at any n. It's not just about large n. And so we see that that mn should scale like some mu to the n. There could be, there must be this exponential behavior, but there could be other behaviors. There could be also some n to the gamma, for example, etc. But some prefactors that don't dominate, but the dominant behavior would be exponential. But it could be addressed, as I said, by some power law. And this mu is bigger than d and smaller than 2d minus 1. And for the usual random walk, mu was exactly 2d. Okay. So what does it mean that there could be this? It could be, say, exponential of minus 2n times n squared, right? So there is some power law correction. But this is really power law in the sense that what is mu? Mu is defined, what is mu? Log mu is defined as I take log of my mn, I divide by n, and I take the limit when n goes to infinity. Right? And all these power laws and so on, they go to 0. And this, in this way, I extract mu. In this sense, mu is what dominates, is what's important. Okay, so before we go on to try to guess what this mu is, so we are going to try to compute this mu and the nu, these critical exponents. I would like to just do a game of trying to do a little bit better, try to improve this bound and to try to estimate this mu a little bit, to try to decrease the gap. Okay. So, because this introduces another useful concept in statistical physics. So suppose we want, so let's just recap that in d equals 2, we have therefore that mu is a number between 2 and 3. Right? Now here is another class of walks that is definitely smaller than the self-avoiding walks, but not as restrictive as moving in the octant, which is I could start here and now always start moving up and never walk down. This is one example. So this is more than just moving in this quadrant, right? This includes those. So these are called, I think they are called, never look back self-avoiding walks. So just, okay, probably it's more reasonable to put it upside down, then it's like a polymer with gravity. You have a polymer hanging, right? That's more natural. But here, okay, it's going up, and it never looks back. Okay, so here's a problem. And now we would like to ask, how many are there with n steps? right, of this. Okay? What we are going to show, so let's put here spoiler. It's not really a spoiler because it will be in 5 minutes, is that the mn scales like 1 plus square root of 2 to the power n at large n. And therefore, we can immediately improve our bound and say that this bound here will be improved right away to 1 plus square root of 2 mu 3. Wow, yeah, so this is roughly 2.4. I'm a bit confused by this 3. Yes. Why did I say 3? Yeah, it looks at 3. Confused. Should be 5. This looks like too small. Sorry, 1 second. If I am in 2 dimensions, I have 3 options. Okay. How much is 1 divided by 0.3? That's 10 thirds. 10 thirds. Okay. Okay. I think the value we'll get from RG is like 3.1, which is clearly not very good because it's immediately ruled out by very basic arguments. But okay, I'll also tell how to improve the approximation. I guess that's okay. Funny, why did I think it was 5? Okay, no problem. Okay, so here is what we know about this mu, the number of paths. So it's some number between 1 plus square root of 2 and 3. So let's see how we establish this result here. So I'm going to show you how to count these walks in 2 ways. Now we are going to count them, and the first way we are going to use the method of recursion relations. And in the second way of generating functions. So both are very useful to know. So if you never saw them, I think it's a good toy model where we can learn these things. Yes?
I think the discrepancy that you find in these 3 is because in your bound, you should have 2d minus 1 to the n minus 1 rather than n, right? Because you already made a choice of 2.
Yeah, but that doesn't matter. That doesn't affect anything.
That had like 3 plus log of 4 thirds.
No, that n minus 1 is just affecting the prefactor. You are right. Andreas is right. At the first step, we had 2D options, so it's n minus 1. But he's wrong that it matters because it's 2d minus 1 to the power n. It's just, it didn't change the exponents. So. Okay. So let's count how many there are using first recursion relations. So here is, so what we want to do in these recursion relations is to write something where mn plus 1 equal to something in terms of how many there are with mn. But the way this works, what makes it easy is to notice that we could write mn as vn plus hn, where this would be the paths whose last step is vertical. For example, that one. The one on the left. This one ends with a vertical step, or it ends with an horizontal step. Okay? And this would be a path like this, where the last step would be, better not to do it here. This would be something like this. Okay? So this is an example of one such path, and that is one example of one that ends vertically. Because you see that when you write it like this, it's pretty clear that how many paths there are with n plus 1 steps that end up vertically. And I can write immediately the following. I can say that if I remove that step, I remove the last step, right? I remove the last, and either I end up with an horizontal path like this, or if it was ending like this, I end up with a vertical path. Or said differently, if I have any path, I can always at the end go up a bit. There's nothing obstructing me from doing that. And so, the number of vertical steps with n plus 1 is equal to hn plus vn. So I have any path, I add one link vertical, I get a vertical path. Or the logic from the other direction, if I have a path that ends vertically, I remove that edge, and either it ends up horizontally or vertically. What about horizontally? N plus 1. If I have an horizontal path, like this, I can always continue and get a bigger horizontal path. But if I have a vertical path, I can now make it into horizontal by continuing the path here or here. So there are two options. So there would be plus 2 Vn. And this would be the recursion relations. This would be the recursion relation. And so this tells me how many paths there are and how many paths there are with one step which are horizontal. There are, say, 2, and vertical steps with one step, there are 1. So we have a starting point, we have a difference equation, so we know all paths, and we know mn plus vn. Okay. So this I can write in this language. I can say that I can think of a vector which has component vh at position n plus 1, and I say that this is the vector vh at step n times a transfer matrix T, where T is the matrix. Let's read it off. So vertical gives 1, horizontal 1, and horizontal I want 2 and then 1. Right? And therefore, my what are the eigenvalues of this matrix? Well, I compute determinant of T minus lambda identity, and this gives me lambda minus 1 square minus 2, right? Which gives me the value I said, which is that the paths scale like 1 plus square root of 2 to the n. Okay? So if you want me to do it a little bit slower, but if I write that my vector vh is equal at position n is equal to a. Okay, sorry. 1 second. Let me find if there is a clever way of doing this even faster. Just 1 second. Then plus Vn So VH at position n is just t to the power n minus 1 times VH at n equal 1. Right? I just applied n times to go all the way from n equals 1 to n equals n. So if I write this original vector, which is the vector 2, 1, I write this as A times eigenvector with eigenvalue lambda plus B times eigenvector with eigenvalue lambda minus, where lambda plus minus are the two solutions to this equation. Right? Then this is equal to A lambda plus to the n minus 1 times lambda plus, because lambda plus is an eigenvalue. This is a two-dimensional vector. I can always decompose it into two eigenvalues. Plus B lambda minus to the n times eigenvalue lambda minus. Right? But what matters is the biggest eigenvalue. So if plus minus correspond to 1 plus minus square root of 2, it's lambda plus that matters at large n because it's the biggest. And the total number of paths is just the sum of the two components times lambda plus to the n. So the behavior at large n scales like lambda plus to the n, which is 1 plus square root of 2 to the n. And it's always this. Whenever you have a transfer matrix and you want a large effect of acting with the matrix several times, that is given by the largest eigenvalue of the matrix, because compared to the largest eigenvalue, the other ones are exponentially smaller. Right? So if I factor out lambda plus to the n, this one is lambda minus over lambda plus to the n, which is super small, which is going to 0. Okay? This problem, you see, would work if I had more equations, then my matrix is bigger. Then instead of 2 eigenvalues, I have 5 eigenvalues. I take the biggest one, and it's what governs the large distance px. The fact that it's two-dimensional in this particular problem is, of course, not important. There is another, okay, this is one way of doing it, which is the one that generalizes to any model. I can always do it in another way, which is by just noticing that Hn is this V's. I plug Hn and Hn replaced by V's. Now I get a single equation for V's, right? Which has V's with many shifts. And I just make an ansatz. V equal lambda to the n. I plug it into this equation, and it gives me a quadratic equation for lambda. Right? That's by substitution. That's the more straightforward way, but the one that would be a pain to generalize if you have many variables. Right? Again, it's a bit slower. I just said that you can take h from this equation, plug it here. Now you have just a single equation for Vn's with many shifts. You would plug an ansatz V scales like lambda to the n. You plug it here, and you find lambda plus minus, and you take the biggest one, and that's the large n behavior. Yes?
The first equation that you wrote, that Vn plus 1 is Hn plus Vn.
Yes.
And when you remove one side, when you come to the horizontal, don't you have two options there as well? Y is in 2Hn.
So if I have a path that ends up vertically, right? It comes, if I remove one step, it comes from an horizontal path or a vertical path.
But you have two options in the horizontal path as well.
No, but I think if you want to count like that, it's the opposite direction. If I have an horizontal path, how many ways are there of getting a vertical path? Just one. I just put the stick.
Oh, you chose the direction that it can only...
Because it can only go up. It can never go down. Right? So that's key. How would we do this counting for a real, honest, self-avoiding walk? We would not. The usual self-avoiding walk is not Markovian. It's not just depends on the previous thing. It's super complicated, right? I don't know. It depends on what happened 1 year before when the walk was passing by some point. It's not a transfer matrix problem. Okay, good. So that's one way of estimating this lambda plus minus. The other way is using a generating function. So let me describe that other way of solving this same problem. Okay. So now let's solve it in a second way. So the first method was a transfer matrix method or recursion relation method. And now with the generating function, which is the same thing, of course, but it's it's just useful to know these tricks. What we would do is not consider Mn, but we would say that I put some chemical potential Zn, and I will study this object from n equals, say, 1 to infinity. I'll try to compute this object. So what am I going to do? I'm going to say that whenever so I went up, say, first, for example. Let's say first we went up. And now there are two options. I can go here and I can go any number of times. Right? Because now we don't truncate. We don't say how many steps there are. We just put some chemical potential and some overall possible paths. So this effect of this dashed line, if I want to count how many steps I gave, what I'm doing here is a sum from n equal, say, 1 step up to infinity of z to the n, which is just 1 over 1 minus z. So that's just a function that if I expand, I get coefficient 1 for each power of z. Just tell me how many steps I gave. So what we would do is say that I have at height h height. How do I write height? At height h, I reach height h, and now I choose what do I want to do there? Do I want to stay quiet and then just go up, or do I want to first walk a little bit to the left or to the right? So at step h, I would have a contribution to my partition function, which would be 1 from doing nothing plus twice divided by 1 over 1 minus z, which would be left or right. So that's what I do in step h. At step h, either I go to the left a bit or to the right a bit, or I do nothing. Right? But now, to go all the way to step h, each time I go to one step, to go to step h, I pay a factor z to the h. That's how many steps I need to go to height number h. And that counts the vertical links. And I did this at each stage, at each floor. So it's this to the power h. And what I should do is sum this from h equal 1 up to infinity. And this is my partition function g of z. And if you compute this g of z, it gives 1 divided by 1 minus z1 plus 2 divided by 1 minus z. And this partition function is, as we said, the sum of mn z to the n. So you just need to compute the Taylor expansion of this function. And the Taylor expansion of this function is nothing but 1 plus square root of 2 to the n plus 1 minus square root of 2 to the n with some coefficients. And from there, you read off the large distance behavior of the number of walks. Okay? So at each step, I choose left or right, and then generating function for walking. Here, I don't move. I just at height h, I don't move left or right, and then I continue to the next step, next floor, and at each floor I choose what I do. I do it at each step h, I sum over all possible steps, and in this way I'm counting, I'm creating a generating function that keeps track of all possible paths. Okay. Now, let me just remind you. So this is some fun problems. So we could now wonder, can we do better? Can we try to find, for example, so we improve this bound. Can we find some paths that we can still compute that are a bit bigger than 1 plus square root of 2? Or can we create a subclass of paths that definitely contain the self-avoiding walks, but which are smaller than 3? Can we try to squeeze it just by simple combinatorial arguments and get better than 2.4 and better than 3 and try to squeeze this value? Right? So I could not. I tried a little bit. This morning I woke up and I thought of paths that go away from the origin and that always are further from the origin. Right? This contains these paths. Right? These paths, they are always further from the origin each time you move. But the paths that are further from the origin are more general than this. It's like they can go further, but you see? They can go further from the origin, but not necessarily going up always. Right? So, yeah, so I woke up like 6 in the morning, I started computing, I suffered a lot, and then it has the same critical exponent. It's still 1 plus square root of 2. So, which is kind of obvious a posteriori. Okay, I shouldn't have got out of bed, because if the paths that dominate are the very big paths, so when you are very big, it's like you are just getting away, so you don't know if you are in a sphere or if you are in a plane. It's like the fact that we don't see that the Earth is round, right? We just, if there are paths that always go away from the center of the Earth, okay, whether the Earth is round or flat, it'd be roughly the same locally. And eventually global, it's a bit different, but from a point of view of counting, it's not so surprising. Okay, so you could count. It's a tougher exercise, but we could define some paths that are always deviating from the are always further away from the origin. So right, paths like this that contain those for sure, right? Because here I can start doing one of those paths, etc. Right? So here I can insert a never look back path, but it's more general than that, because if I am here, I can now put a never look back path, which is in a different direction. And then I turn, and here I put another one. So provided I'm getting away from the origin, I could put these paths, but this number of paths scales like 1 plus square root of 2 to the n, so it doesn't improve our math. And it would be nice to think if something generalizes that 3. There is a way of doing a little bit better than 3. But it's tough. You can, I think I encourage you to play a little bit and to give ideas, but I could not do it yet.
Does this transfer matrix or generating function approach generalize easily to higher dimensions?
It depends. So first you should think of a problem of this never look back that is also Markovian in this sense, that if you know the last few steps, you know what you can do or not, right? So for example, if you are going horizontal in this direction, it's enough to know that you cannot go horizontally back in this case. So you should first generalize the paths to higher dimensions. If it has this property that at each step I only need to know the last or maybe the last 2 steps, then yes, you can write a transfer matrix. But if you just say that it's, for example, 3-dimensional walks that do not go back, that do not go down, that definitely you cannot. Because when you reach a plane, that would be the usual self-avoiding walk there. And then you would go up, and then usual self-avoiding walk in 2 dimensions. And usual self-avoiding walk is what I'm saying is hard and you cannot solve. Right? So it cannot be just this, that it goes up and then does self-avoiding walk, then up and then self-avoiding walk, then up and then self-avoiding walk, because that is solving the two-dimensional self-avoiding walk several times. And that's hard, right? But it could be a generalization of where instead of just going up, it only goes up and right, and in the other direction we have freedom. Then yes, then you could apply this method. It's models that never look back or left, but otherwise they go up and down, for example. Yes?
What do you mean when you say that this path never, like, is always going away from the origin? Because it looks to me like some of the segments are getting a bit closer, like in terms of...
Yeah, then it's because I did not draw it properly. So I can explain. I mean, this didn't pan out, so I don't want to spend too much time with this. But let's draw some distance from the origin.
Are you using that metric?
Sorry?
Are you using the taxi metric?
I'm saying these guys are at distance 1, distance 2, distance 3, distance 4 from the origin.
Okay.
Right? And then what are these walks? I start here and I choose any direction, right? And then at this step, I choose, do I go clockwise or counterclockwise, and how many steps I go. For example, I choose I go clockwise 3 steps. 1, 2, 3. I stop. Now I choose, how do I go to the next layer, for example, like this. And now here I choose how many steps do I give in this circle. And I go 5 steps counterclockwise. 1, 2, 3, 4, 5. And now I go to the next layer. And then I choose how many I give in this layer. Okay? So this problem is a bit funnier to solve. I solved it, and it's still 1 plus square root of 2. Okay? You can play with it and solve it and think that it would be more than 1 over square root of 2, and it's still 1 plus square root. If you find something that's better than 1 plus square root of 2, I would love to know. Okay. So
Has someone studied these random walks but with relativistic particles? Are they?
no, I have no idea. I mean, I don't do statistical physics. I just statistical physics for me is just to torture students. Yeah, I don't do it for a living. Yeah, it's I know nothing about literature. Yeah. Okay, no, I have no clue. Okay, so right. So we see already in a few examples that introducing a chemical potential is useful. So, and I just want to remind you that introducing chemical potential is equivalent to fixing the number of particles. And the reason why is exactly the same reason why it was the same as working at finite energy or finite temperature. Because the paths that dominate anyway, if some paths dominate, when I sum over paths, they will be picked around some very special n that will be a function of k. So working at fixed k or at effective n that is fixed by k is exactly the same thing. Okay, so let me just remind you how this goes. For example, I could consider the generalization of that mean displacement that now I would call correlation length at fixed chemical potential mu. And what would this be? This would be something like this, where I sum over all paths n, right? And then I, or maybe better, I sum over all distances r, and then I sum over all paths n of n steps that go from 0 to r, and I average r square times mu to the n times how many paths there are. I was using the notation there, omega, how many paths there are that are now self-avoiding walks that go in n steps from 0 to r, and I would normalize this by the same thing where this r is replaced by 1. And so what's happening here? What's happening here is that in this sum, we have a competition of two effects. We have mu to the n that decreases exponential. This would be mu to the n with mu smaller than 1. And we have the number of self-avoiding walks that grows exponentially. This would be how many self-avoiding walks. It grows with some exponent mu that we know is bigger than 1 plus square root of 2 and smaller than 3. And so what happens is that this function is very strongly picked around some critical n0. Right? And this would be an n0 that would depend on mu. And so working at fixed mu and right. Okay. Right. And therefore, this quantity here would be equal to what is the expectation value of my r square at this n0 that is a function of mu. So working with, so we use different notation conventionally. This we call the scattering length at chemical potential mu. This we say the displacement, the average displacement for n0 for n0. But there is a translation. If you know this function n0 of mu, you can just translate back and forth, exactly like going between ensembles in canonical versus microcanonical. Yes?
What's the vertical axis?
The integrand, the summand, as a function of n. Okay. For example, I want to point out the following, that at large n, we saw that r, we defined an exponent nu. We said that r scales like n to the nu. Right? Nu was a nice exponent. We computed this 1/2 and 1, and that was something nice to compute. So that will translate, r goes to n to the nu. This will be equivalent to saying that this psi will behave as 1 over mu minus mu critical to the nu. And that's what I'm going to explain now. So diverging with length to the power nu is the same as diverging with chemical potential when you approach a critical point to the power nu. Okay? So this is just a translation that these ensembles being equivalent, it implies this relation. Because what we are going to do next is extract this guy and this guy in this language using RG. Right? So next, so first I will explain this. And next, we extract nu and mu critical from RG, and therefore we learn by this map, we learn about R scaling as n to the nu, we learn about the critical exponent we want. But first we have to establish this map. It is just something simple. Right. Let me, sorry, I apologize. Because mu we already used, mu. Mu we said it's the way, yeah, this was a bad notation, sorry. I want to change the notation. So forgive me. So, yeah, this was, okay, that part is a different lecture, it's okay. But here, I don't want to use mu. What letter do you want? K. I think we used K once. Here we have K. Then this is k to the n. And this is omega n that scales, as we said by definition, is mu to the n. Okay? And here, the parameter is k. So k, n0 of k, sorry for changing here. And here, it's k minus k critical. Okay? Chemical potential is. So we are going to extract this critical chemical potential Kc. So what do we have more precisely in this plot, like you were asking? So this summand is what? Is, as we said, is k to the n, mu to the n from this omega, and some power law behavior, say n to some power, that would come, for example, from this mn, these prefactors in the law. So n to some power law smoother function. And therefore, the saddle point, which is what we are doing in this figure, at the saddle point, means that the derivative with respect to n of the exponent is what? It's n logarithm of k mu plus something log n should be equal to 0. And that, you see, implies that n is proportional to 1 over log of k mu, which behaves as 1 over k minus k critical, where k critical is 1 over mu. When k is approximately 1 over mu, this log is 0 and it vanishes like this. Is it clear? If I write k as 1 over mu plus k critical, then I get this behavior right away. And so we obtain what we want. That the translation is that close to the critical point, n is the inverse of the deviation of the chemical potential from a critical chemical potential. So we learn that mu is related to a critical chemical potential. Mu was related to how many, to the number of paths. And now we see that this number of paths is related to a critical chemical potential. And the theory only makes sense if my potential is smaller than the number of paths. So if I'm summing with a chemical potential, if the chemical potential is not smaller, if the chemical potential is not smaller than this critical chemical potential, the entropy wins and the paths start becoming infinitely big, and this just doesn't converge, right? I just create bigger and bigger and bigger paths. Okay? So mu is related to the critical chemical potential Kc, and n is identified with the deviation from the critical point, and therefore r behaving like n to the nu is equivalent to psi behaving as 1 over k minus k critical to the nu. And so there is a translation between the values that we'll find in the close to the critical point and the critical exponents that we were after. Okay? Good. So the conclusion is that there exists a critical k equal to Kc, where the correlation function, the correlation length, diverges as psi is 1 over k minus k critical to some power nu, where this nu is the same exponent that appears in R scaling in number of steps to the power nu. And for the random walk, nu was 1/2. And for this theory, we are now going to study it through RG, because RG is ideal for finding critical points, as you remember. We look for fixed points under zooming out. And when we find this critical point, this is exactly what we are after. Okay. This is amusing. I wrote here in my notes 2.4 smaller than 3.36, smaller than 3. Okay. Good job. Oh, yeah. Okay. So,
I have a question.
yes.
I lost track of what is the physical interpretation of K and
Okay. So there are two things. One is that putting K, you lost track of the difference between K and mu? Sorry, so okay, that was my fault. So let's remember, let's emphasize that because it was a mess in it. So K is a chemical potential and introduced to weight paths of length n as k to the n. We just said I sum over paths of length n comes with weight k to the n. In other words, that is log k, I can think of it as some energy density of some polymers. Right? Because if the polymer has length n, it would cost some log k, that would be like that. Mu was defined as how do the number of paths of n step scale as n goes to infinity. It was related to the degeneracy of the self-avoiding walks. How many paths are there? And what we see is that this number, right, that we know is between 1 plus square root of 2 and 3, right? Because these are the ones that at each step don't go back, so it's definitely more than self-avoiding walks. And these are the ones that never look back, that's smaller than the self-avoiding walks. So it's in this interval. But what was nice is that we saw that this mu is actually equal to 1 over a critical Kc, where this is a critical chemical potential. What does it mean? Fixing K is the same as fixing N. That's just by the usual reasons that we saw before. Saddle points say that large, if you work at a fixed but large N, or if you work at fixed chemical potential, it's the same, doesn't matter. So fixing K is fixing N, right? What's the precise relation? We don't know, but we just know that it's equivalent. If I know fixing K, I fix N. But we did know that large N should correspond to K close to Kc, in the sense that the map was rather sharp in that case, that up to some constant that we don't know, a constant over K minus Kc is equal to the N at that chemical potential. And so being at a chemical potential close to Kc means studying dynamics of very large walks. Okay? Right. So if the chemical potential is 0, for example, then I have the walks of 0 size. If the chemical potential then increases all the way to K critical, I increase the size of the walks up until the point where they diverge at the critical temperature. Okay. Right. So now, the idea is we will do RG. Namely, we will try to integrate out a bunch of steps. Right? So what we do is we integrate out a bunch of steps and we reduce this to some effective step. Like for the random walk, for the usual random walk, we said that I just take some path and I just replace this by some effective step. And the idea is that with the RG, with the renormalization, we will start studying the large distance behavior, which is what happens when K is close to K critical. So let's try to do it. So now there is a problem, which is that whereas here we could do it exactly, in the self-avoiding walk we cannot. We need to do some approximations. So here is what we are going to do. So I'm going to say the following. I want to say that imagine I have a lattice and I take this as my building block. Right? So the lattice continues in both directions. So the lattice is obtained by taking this block and putting this block several times. So I just take this block and reproduce this block everywhere, right? You see? And you see the way I'm drawing, I'm putting lines getting out here and here, but not here and here, not to double count. So it's literally you take this and you copy paste many times and you get the full lattice. So the edge, this edge is here, this edge is here, this edge is here. But this bottom edge here is not, because it will be when I put it down here. Not clear. Yeah? It's clear? So if you just repeat this block, for example, I'm going to repeat it in green here. So I will just put it here. You see now the lattice is bigger and I put it here. I put it everywhere and I get my full lattice. Don't be, of course, this is not bigger, right? This is the same. These guys are like, so I pick this, put this, put this. This is the full lattice, right? And what we want to do is replace these things. So I have here, etc. And we want to replace this to coarse grain and replace this by just this, by just 1, 2, 3, 4, 5. Would like to replace this by a smaller lattice by replacing, for example, let me give you an example, a path that would go like this. I start like this, and I do say this, this. Sorry. I don't want such huge block. I want to do something a bit simpler, sorry. Okay, we could do this. This is actually, no, sorry. I will erase. I want to do smaller blocks, sorry. Yeah, sorry. I want to do like this. So I want to repeat this block. So this is a smaller block. So the claim is that my lattice is built out of this. And then, and this would become, after renormalizing, I would integrate out and reduce it, all these 4, by just a single one. And then there would be the neighbors, of course, that would be here, and so on. And the question is, what happens as I do this procedure of integrating things out? Okay. So now let me explain what I mean by this. Here, microscopically, I have many paths that after I integrate out become the same path. For example, I have this path here, right? This, for example. I want to say that what is this path? It's a path that came from the bottom and left at the top. So this path, after I do RG, I think of it as a single step that just removes these 2 links by just going up. Okay? So let me explain, let me write a precise equation for what we want to do. So in an equation, we want to say that if I have this path, for example, it's going to become, after I replace it by a single line, it becomes just this. So I just zoomed out and replaced all those edges by just 2 edges, and then that would be just going up. But other things would be replaced by that. Many things would be. The RG is integrating things out. So this path, for example, that goes also from a bottom link to a top link would also be replaced by that. Right? And I would sum them. And then we will see in equation what this is. And another path that would go there would be the one I drew there as my first example, which would be this. And another one would be this. And another one there are 8. The other one would be say this. And the other one this. So all these paths, oops, to draw it here. All these paths, and then the last ones, which are the most complicated ones, would be this. These are the biggest ones here. And finally, and the idea would be that here, in my original model, I added up all this. So what was I adding up? Here, I have 2 steps. So I have k square, and there are 2 diagrams, so 2. Here, there are 1, 2, 3 steps, so k cubed. And there are 4 diagrams here in the middle that have 3 steps, so 4. And finally, I have 2 diagrams which have 4 steps. So that's how I would weight this. All those configurations, this will be the total weight for them. Okay. And what are we saying? We are saying that this is defined to be my effective K prime. Right? In other words, what we are saying is that as I'm zooming out, right, here I have many paths here, for example, like this. And now after I zoom out, it became just going up. And then there were here many paths I could do here. For example, this, and it became just another step going up. But to keep track of how many were there that I integrated out, when I'm integrating out, k prime is not k, but k prime is that function of k that tells me how many ways there were for this effect to be going from up to down. Now, it's super important to emphasize this is an approximation. It's an approximation, for example, because there were paths that don't have a sharp figure what it means. So, for example, take a path where it goes up gets inside and then comes down through the same edge. Right? So a path like that existed before, so this is after RG. So here it was clear what to do. But what about a path, say, like this, where we just start here and say that I had this path here. This could have been part of a self-avoiding walk. It's a walk that said, I'm going up, oh, and I change my mind, and I go down again. Right? And this path, what am I going to replace it with in my final one? I could just say nothing, for example. I could say, well, if you change your mind, I will ignore. I will pretend this never happened. Right? It's like you enter the door, sorry, not my meeting, and you get out. Okay, fine. Don't worry about it. Right? So we are ignoring some configurations, assuming they are not very important. And we are thinking that this model with, if I have a lattice of L sites, L by L sites, and I study my polymer with chemical potential K, the idea would be that this would be related to a model where I integrated out, so I now have L over 2 times L over 2 sides, because whenever I had 2 sides, I joined them into one, right? So I coarse-grained, I divided everything by 2. But now, in this new lattice, I have a polymer with effective chemical potential K prime that depends on K. So if this works, it's a great improvement, because you start with million by million, and you say this is like half with some K prime, which is half with some K prime prime, half, and you do it a few times until your lattices instead are reasonable, like 20 by 20, 30 by 30. Right? So if this works, that would be the idea, that this model with chemical potential K is equivalent. It's equal, because all we did was integrate things out. So we wanted the configuration. We sum over all configurations, we did it, and the sum over configuration translates into some effective K at larger scales. Because we no longer care about things that happen very close. We just say every 2 lattices let me replace by 1, then every 4 lattices I replace by 1, then every 8 by 1, if I do it many times. It's like not caring about the details. And you just say, if a walk does like this, okay, that's just going up. Right? And you start coarse graining in this way, but then you have to replace K by K prime. Okay, is it clear? Now let's study this transformation, K going to K prime, because it's actually quite an interesting transformation. Okay, so let's do it. Let's plot this K prime as function of K that we got. It's a polynomial. Polynomials are easy to plot. So you see that K equals 0 maps to K prime equals 0. And then if K is positive, the left-hand side is never positive, is never 0, because it's a linear combination of positive coefficients. So the zeros of this polynomial are for negative values of K. So this polynomial is something like this. There's a bunch of zeros. And this would be K prime. And this would be K. Huh? Okay, good. And now let's draw the line here. Let's draw a line. K prime equal K. And we see that there are nice things happening here. Suppose you start at some value K, right? So you start at some value K. Let's start, say, here. So you are at this value K, and you are mapped through the first step of RG, let's say RG1. You are mapped here. Now you are at this effective K prime at a lattice that is twice as big. In other words, you have half the number of sites in your lattice. But now you want to do it again. So what does it mean to do it again? Now you take this value, k prime, and you iterate it again, which means you go here to this value. That's the value where k is equal to k prime. So, and then you ask what's the value, what happens when I map to this value? So you go here. That's what happens if you apply it twice. This would be doing 2 steps of RG2. Then you ask what happens if I apply it twice. So you take this k and you plug it into the machine again and you iterate and you go here. So in this way, you see that k prime, if I apply that function k prime of 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 some initial k, it's equal to 0. So I move several times and I go to this point. So this point is the point k star equals 0. It's one fixed point. So this is a boring critical point. It's not interesting, this one. It's boring, and it corresponds to finite walks. It's just walks, which do 1 step or 2 steps. If mu is very small, you are going to do very small walks. Okay? If on the other hand you start here, you start at some value k initial here. So this is if k initial is to the, this is for k initial to the left of the intersection point. To this, in this part, to the left of this intersection point. If k starts to the right, I start here, I go to this value of the curve, right? And then that k prime I apply again. So you'll see what happens that you apply several times. And if you start here, you apply several times, you go to infinity if ki is to the right. So if you start at k, which is bigger than a critical point, which would be this point here, k critical. So those will be very different walks where the chemical potential is very big. So these are finite walks. So this is dominated by boring walks, like you do a walk like this, and you stop. Whereas here, when it goes to infinity, this would be very interesting walks that would occupy all the lattice. It's like lattice filling walks. So it really, the chemical potential goes to infinity, like no space is unused. So this would be some lattice filling walks. You see that when the chemical potential is very large, compared to the one where you use everything, any link you don't use, you are suppressing compared to using everything. So this is, you consider configurations that without self-intersecting cover the full plane. It's interesting, perhaps. That's the more interesting, this is a more interesting critical point. And we see that Kc, if we sit exactly at Kc, at k equal to k critical, we stay there. We apply. It's a fixed point by definition, right? It's when k prime of k critical equal to k critical. So if I apply several times, I stay there. And we see it's unstable. It's unstable because if I start slightly to the left or start it to the right, I go away. And this instability is exactly the existence of a relevant deformation. So I have to tune. I have to tune my chemical potential to be at the critical point if I want interesting behavior. Okay? So at k equals c, we get an unstable point. which just means that it requires tuning, like usual. But this is the interesting point we want to study, the one where as we are approaching this critical point, the lengths are becoming bigger and bigger. So we can compute it. So let's solve that equation. So k prime is equal to this, which is 2k squared plus 4k cubed plus 2k to the 4. And if you impose that this is equal to k, right, this is to find the critical temperature, this gives you that a critical temperature Kc is 0. The 0 is at 0.297. Okay? Now, I just realized, as I told you in the lecture, that that doesn't look good because 1 divided by 0.297 is bigger than 3. So as I promised, this was an approximation. And clearly we see it. You should be worried that this approximation doesn't seem that good because it's already violating the most basic bound that we said. So it's giving like too many paths. So we could be worried. So this would mean that we could be worried because of this. But on the other hand, these critical positions are not universal anyway. Right? As we know, the exponents are universal, but the precise values of the critical exponents should not be universal. So we could still close our eyes and say, let's see what the critical exponents are. Perhaps those are a bit better. But definitely the critical temperature doesn't look like good. Okay? So what could we do about this critical temperature before I go to the critical exponent? What we could try to do, is do a better normalization. We could ask, what happens if I do what I was drawing, which is instead of renormalizing this, I do it integrating more things out, where I integrate all the degrees of freedom not only in 2 sides, but in 3 sides. So what happens in 3 sides? In 3 sides, I can go directly like this. For example, that's one term that gives k cubed. Or I can do a very complicated path, like say this. And this would give 1, 2, 3, 4, 5, 6, 7, 8, 9, like k to the 9. So we get a bunch of terms from k cubed all the way to k to the 9. Now many configurations we are taking into account, right? And for each of them you count how many ways there are, like doing the exercise we did. And this would be my k prime. And we could check if this k prime is better than k. This is supposedly, the more degrees of freedom you take into account, the better the approximation should be. I did not do this computation, but the question is if Kc from this exercise where we make a dilatation by 3 is better. That would be a question to ask. If the renormalization group is becoming better and better as I'm integrating things more carefully.
Is the problem coming from those paths that we ignored?
Probably, yeah. That's probably what's happening, yeah. It's yeah. In other words, as we are integrating things out, we often generate new couplings. So I had only one coupling, which was the length. I only need to measure the length. But what can happen is that when you integrate things out, it's true you can always integrate out because you just sum over configurations that are smaller. But perhaps after you integrate out, you need some effective coupling that measures, say, the curvature of the path. Because for the same curvature, there were different the number of microscopic paths compatible with that curvature was different. So whereas in the original model, there was no coupling, no chemical potential that was conjugate to how many turns and counter turns you do. Because microscopically, the number of doing a turn or going straight, maybe there are different number of ways of doing it. It could generate a coupling under the normalization, which would be an effective coupling that would be generated. Okay? So this would be like if you have a spin model, and I have the neighbor and the nearest neighbor. Normally, the next to nearest neighbor, they were not interacting. But as I'm summing over nearest neighbors, I generate effective interactions that, as I do RG, will become longer and longer range. So in the language here, it would be that as I'm zooming out, the effective description, to properly describe it, I could want to enlarge my space of couplings, which I'm not doing when I'm ignoring these paths that go back and forth. Okay. Okay, so that's a question we could ask. If I integrate things out more, I generate this polynomial. So k cubed, how many paths there are with 3 steps? It's 1, 2, 3. So this one is easy, 3. But we would work out the combinatorics of all these terms. We call this k prime. K prime equal to k gives the critical temperature. Hopefully that one is bigger than 1/3, so that it doesn't violate this. Okay. So this gives, by the way, if you want, this gives 3.36. And 3.36 is bigger than 3, contrary to what I wrote in my notes. Okay. But what's interesting now, and I'm going to go a little bit over time today, exceptional. Which is now we could try to estimate these critical exponents. Which is given by studying the correlation length close to the critical point. So notice that you have some correlation length, some average size with some chemical potential K, right? Which tells me what's the average size, right, of some polymers. And that's the average size, right? Measured in units of 1. Now we did a dilatation. And what was the size of the polymer? Well, the size doesn't change, but now I measure things in steps of 2. Right? So the polymer was the polymer, right? It's a polymer, it goes from here to here. For me, originally it was 200 lattice spacings. But then I did RG, now it's 100, because each 2 steps were replaced by 1 step. So under the RG, close to the critical point, what I will have is that the correlation length, the size of my polymer, right, after I coarse grain, I have twice as few steps. So the number of steps in the original lattice is 2 times bigger. So lambda, where lambda is by how much I rescale, is 2 in this case, times the correlation length measured in the second model with chemical potential K prime. Okay, so this would be close to K equal to the critical temperature. And therefore, we would conclude, close to the critical point, that 1 over K minus K critical to the nu would be equal to lambda, lambda is 2, times 1 over K prime minus the critical temperature to the nu, which is lambda times 1 over K minus K prime to the nu times 1 over derivative of K prime with respect to K at K critical to the power nu. Right? So K critical, this K prime is K critical plus the derivative. So This is the definition of derivative as I'm expanding. And therefore, we nicely see that these terms cancel. This term cancels with this term. And we conclude that nu is equal to, this is equal to 1, I take the log. So nu is equal to log of 2 divided by log of the slope of my transformation dk prime dk at the critical temperature. So I just have the critical temperature, I have the slope there, I can compute this. This is 2. This I can compute at the critical temperature, and this gives 0.771. Okay. And this is to be contrasted with the exact result, which is 0.75. So this one is better than our critical temperature in this. So this, in 2 dimensions, it turns out that this is exact. In 2 dimensions, we know this exponent. And we see that the RG is now giving a very good estimate of this. So a question is, so what would happen now in this example that I suggested that you guys do? Actually, I saw this suggestion in a book where I took this from. I can then give you the reference. He also suggested to do this, to just do it on 3 by 3. Maybe enumerate all the paths with a computer, or maybe do it by hand, I don't know. But it goes from k cubed to k to the 9. You get k prime. And what changes in that? Nothing. It's the same thing. The only thing is that, of course, in the new example, we had here our k prime of k was a polynomial, right? Of what degree? It was k squared. It was polynomial of degree 4 in k, right? And now in the example I'm suggesting you to do, where you integrate a bigger lattice, this would become 3. We are integrating more things out. And this 4 will become 9. And you will have a more complicated polynomial. So I would expect that there will be a bunch of boring things happening, and then something like this. And you will have, again, some derivative to compute here. And that you would compute in this new polynomial of degree 9. And hopefully, in this new exercise, this becomes closer to this value. And the critical temperature starts taking reasonable values. That would be the hope if things are systematically being improved. That you would integrate out more things. And the hope is that in doing this, this would become closer to, even closer to this value. But we are already impressed that it is so good. Okay. So finally, just to conclude, let's go to the definition of this correlation length. Where is it? It's here. Where we have here a summation over n, k to the n, number of self-avoiding walks to the n. That's exactly what we had here. Summation k to the n, where k I call mu, beautiful. Mu to the n, probability of going there. Probability was just number divided by z. And we saw that this was related to the propagator. Right? So another way of studying these self-avoiding walks is by the observation that the summation of k to the n, number of self-avoiding walks that connect 0 to r, is also equal to a propagator, and it's equal to the propagator between spin at position 0 dot spin at position r in our ON model, where we studied O2 in great detail and briefly discussed the other ONs as well, as n goes to 0. So it's a very funny analytic continuation where you start with a vector of n components, and then you say, oh, and then is 0. So you are summing over configurations of vectors of 0 components. Okay? But what happens is that the fact that you have 0 components means that some things that you could do with finite components, like expanding 4 terms that would meet at the quartic vertex, and therefore it would self-intersect. When n goes to 0, those quartic terms vanish. So they project out intersections, and they map you in the same way that here there was no restriction. Here, because of these quartic terms being suppressed by n, you remove intersections, and instead of having usual walks, you end up with self-avoiding walks. So it's very much the same argument that here goes to the walks. Here it would go to self-avoiding walks because self-intersections would be projected out. And therefore, yet another way that we could study these exponents is computing them in the ON model for any n, right? Checking that the computation is good by checking against n equals 2 and n equals 3, because for those we have experimental values. And when it's working, analytically continue n to 0 and learn about the critical exponent of this self-avoiding walk. So that's yet another approach towards this problem of studying self-avoiding walks that one could take. So in the end, as you see, it's another way that these models, these spin models, these walks, and critical exponents, it's all very much related to each other. So, as I said in the last week, this was not meant to be a course on a little bit of each model, but we tried, I hope we succeeded a little bit in going very deep in some specific examples. So if you have to study some other statistical model which is totally different from this, you will know 0 to start with, but I think you will be strong and capable, and you will not be afraid of anything. And I think the models we chose, they are not the easiest ones. So I think if you understood these ones well, you are well prepared now for anything. So I think it's good. Thank you. We are done.